guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to have a review on machine learning and then continue our discussion about deep learning. So this session is for reviewing the machine learning stuff that we talked about it in previous sessions, and those are useful for going through deep learning. Okay, first we start with different types of machine learning problems that we learned. The first category is supervised learning. So in supervised learning, like regression or classification, we have some target variable or some outputs that we know for some data. We call them training data, and we want to train a model based on this training data. So we both have the input features or input data for the model, and also the correct output for the model to train the model. The second category is unsupervised learning. In unsupervised learning, we want to extract the underlying structure in the data. So in unsupervised learning, we don't have any labels. We just have some data in the space, and for example in here maybe we want to find a manifold that these data are on that manifold, or using PCA to reduce the dimension of the data. And the third category, which is probably new for you, is reinforcement learning. So in reinforcement learning, we have some reward for the sequence of actions that we take. For example, let's say we have a football game, and based on some actions that you do, you get some score. But for training the model, you don't exactly have what actions should the agent or should the model do to get the score. But for some actions, you could know that what is the reward for those actions. But you don't have the ground truth for the actions themselves. Okay. We will talk about especially reinforcement learning more in the next session, so don't worry about it so much. Okay. So in the supervised learning, as I mentioned, we have some pair of points. So these are the data, and these are the corresponding labels. So if it is the classification tasks, the y are discrete variables like 0, 1, and so on. But if it is regression task, the y values are continuous. And so in the supervised learning, we want to find a mapping that maps the input data to the output label or output value, because it could be continuous. So we have an input space, which we denoted that by x, and we have the output space, and we denoted that by y, and we use the training data to find that function, and we want to test that function on the test set. Okay, so again in regression, we have continuous target variable. For example, y could be between 0 and 1, but in classification, we want to predict discrete target variables. So for example, we may have a one-hot coding output variable, or just one value, which could be 0 or 1, depends on the number of classes. For example, as you could see in this case, we have a classification tasks. The plus data are related to probably 1 is y is equal to 1, and the minus data is related to the label 0. So in here we want to classify this data, and we learned that we have lots of classifiers to do this, like SVM algorithm, logistic regression, and so on. And this is a regression task. In this case, we have a one feature, and this is our output, and we want to find probably this line or a nonlinear maybe model to describe the output based on the input values. So in supervised learning, we have some data points and their target values, and we want to find the mapping from X to Y. But in unsupervised learning, we have just some data without any label, and we want to group the data or find the structure in the data. For example, we learned how to use k-means to group this data, or doing clustering on this data and split this data into two different categories. So this is one example of unsupervised learning. Okay, now as you could see in here, this is an example of classification. We have different types of data with different target values, which are color coded, and we want to classify this. So probably we want to find this decision boundary to classify these three classes. And in here we have unsupervised learning, or special. In here we want to cluster this data, and we want to, and all of the data are actually don't have any special target value, and just we want to cluster them or find some kind of underlying structure in this data. So unsupervised learning is not just clustering. We also could have density estimation. So in some cases, maybe we are interested to find the distribution for the data. Let's say if we have some data like this, and they comes from a distribution, maybe we want to find the distribution of the data. For example, in this case, it could be a Gaussian distribution that is like this, and maybe we want to generate new data from this distribution. So we could generate some new samples from this data. We will see that this is actually useful in generative adversarial networks to generate some new data. And we have dimensionality reduction, in which actually we want to reduce the dimensions of the data. We have seen PCA, PSNE, and other methods to reduce the dimension of the data. Just note that in GAN we don't find the explicit distribution of the data. We will talk about it later, but just to emphasize on this point. Okay. And so at last we have reinforcement learning, that that we have some actions and some rewards for some of the outputs. So as I mentioned, maybe we want to learn how to play the football match or how to play a special game. In that case, we use reinforcement learning to train the agent. We will talk about it later in more detail. So there are lots of different actual real-world topics, actual real-world tasks like games and other things that really needs reinforcement learning instead of supervised learning, because we don't know exactly what kinds of actions are really useful. We just know at the end whether, for example, in this game, at the end we just know that whether we won or lost, and based on those labels we should learn how to play the game. So I hope that it is clear for you the difference between the supervised learning and reinforcement learning, because maybe it is a little unclear at first what is the difference between them, but we will explain it more in detail next sessions. Okay, so we learned that actually what we care in machine learning is generalization. So we don't want have a model that just overfit on the training data and performs poor on the test set. So in other words, we don't want our model to memorize the training data, but we want the model to figure out the pattern of the data, be able to predict the output values for the new data. Okay, so we have seen that in overfitting. So what we care in machine learning models is generalization. So in the steps of solving supervised learning problem is typically the first step is actually you want to choose the hypothesis space in which you actually select the family of the functions that you allow to learn the algorithm function to, for example, classify between different data. We will see that in an example in next slides. And after that, we should define a loss function to minimize that loss function and achieve the optimized parameters for the model or for that specific hypothesis in the hypothesis space. And we have different methods to optimize that loss function. For example, we could use gradient descent or other methods that we will explain later to optimize the loss function. And at last, we want to evaluate the obtained model by the validation set or the test set. So and for example, in here we could use k-fold cross-validation to evaluate the model. Okay, so this is an example to see those steps in here. So we have linear regression in here. So the first thing is that we should specify the hypothesis space. So if we have linear regression, so the hypothesis space is W0 plus W1x, which is a model with two parameters, and it is a linear model. Okay, so this is the hypothesis space. For example, this is another hypothesis space. Maybe someone says that this is my hypothesis space, the sign of W0 plus W1x. So this is a family of linear things, so this is a hypothesis space of linear regression. And the second thing is loss function or cost function. So in here we use squared error, as you could see in here. This is the output of the model, and this is the label of the training data. So, and the cost function is based on the value of w's. So when we change the value of w, then the value of cost function change, and we want to find the w's which optimize this j of w, or minimize the cost function, which is probably the line with the parameters that create this line. Okay, so if you plot, if these are the data, and if we plot the j of w based on w0 and w1, we have some convex loss function in here, as you could see, because when we determine the data, so these are the training data that we have, and this is the function of just w0 and w1. So we could plot that based on w1 and w0. We have some kind of convex function in here for this training data, and actually we are looking for the minimum point. In fact, we are looking for a line in which this is the optimal w0 and w1 optimal value. So our model will be something like this. So we are seeking to minimize this cost function to obtain and achieve these parameters. For example, if we have this line in here, it has a w0 and w1, and it is in here. So we could, and these are the contours of j of w0 and w1. And as you could see in here, for this point, which is corresponding to a w0 and w1, we have a line in here, but the cost function is not minimum. So the minimum cost function is in here, and we want to get to this point, but now in this point, this is the line, and actually this is not a good line. As you could see here, we are actually looking for this line for this data. And for the optimizing the cost function, we could use an iterative optimization process. Like I said, one way is to use gradient descent. So we actually could start from a point and just update the weights with delta w to reduce the cost function. So we have j of w, and we start from a specific w, and then we update the w based on delta w. We see that how to specify the delta w, and then we reduce the j of w. We will see that we need in gradient descent, for example, we need to compute the slope to reduce the cost function. For example, if the cost function is something like this, let's say this is the cost function and we have just one variable in here, then let's say we are in here, to reduce the cost function, we just need to move in this direction, right? So actually it is related to a slope of this function in here, so we want to move in this direction. But when the point is in here, if we want to get to here, we should move to this direction, which is related to the positive slope in here. Okay, so we want to, actually this is a negative slope, and we want to move in the negative direction of negative slope, which is the positive direction. So we want the direction of the steepest descent method is the negative gradient. So we calculate the gradient and we move in the opposite direction of the gradient to reduce the cost function in an iterative manner. In other words, in each step we update the W as the previous W. This is the gradient of the cost function, and this is just a factor which we call it learning rate, and we multiply them together, and it is just a scalar, and we update the W based on this delta W to reduce the cost function. Okay, and if we move in the direction of minus gradient or negative gradient, this is the fastest direction that we can decrease the cost function. We will talk about the optimization process in really more detail and dive into that in some next sessions, but for now just we want to have some sense about how we optimize the cost function in different algorithms like linear regression. And the assumption of linear regression and the assumption of the gradient descent is that the cost function should be defined and differentiable in neighborhood of WT, because we want to calculate the gradient. And so as we have seen in here, the definition of gradient is actually related to the neighborhood of that point. So in the neighborhood we should have a differentiable point in the neighborhood of W of t. Okay, so this is actually, as I said, we called it step size or learning rate parameter, and the gradient parameter, the gradient vector is actually a vector in which we have different derivative with respect to different dimensions. So in this example, if we calculate, so we had in linear regression we had squared error as the cost function. So if we calculate the gradient for this cost function, we will derive this. So if you apply the gradient descent on the parameters of the model, you get something like this to obtain the model parameters. So if we start from here, which is the W0 and W1, then we should calculate the gradient in here. If you know, the gradient in here is actually orthogonal to this point and in this direction. So we should move in this direction. Then we will go to here, and we have now new W null and W1, and the line is actually slightly changed in the slope. And again, if we go to the next, if again we calculate the gradient and we move in the negative direction, because the gradient are actually in this phase, and we should move in this direction, and it is corresponding to this line. And if we keep on going that, and as you could see here, when we are going toward the minimum, we are getting a better line in each step. So as we reach the minimum of the cost function, we get a really good line. So these are parameters of the optimum function in here that we are looking for. Okay, so this is the gradient descent and how gradient descent works. The disadvantages of gradient descent are, the first disadvantage is that local, it could get stuck in local minima. So if we have something like this, we probably want to be, let's say we have something like this, we probably want to be in here, but if we start from here, then the gradient descent will stuck in here. Why? Because in here the derivative is 0, or the gradient is 0, and so the wt plus 1 will be equal to w of t, and we don't have any update in here, and so on. And if you start from here, you will stuck in here. Actually, you could jump from this local minimum if you choose a large learning rate to have this kind of steps, but we will see that it could make the algorithm unstable, the learning of the gradient descent. Okay, but the point is that if J is convex, for example, in a linear regression, we have a convex function. So the local minima is actually global minima. So we in fact we just have one global minimum. So when we have a convex function, we just have a one optimum point. So this local minima is also global optimum point. And we have some variants on the gradient descent method. So in the gradient descent, we actually we should calculate the gradient over all the training data. But it could be actually computationally expensive to calculate the gradient on all of the data. So in a variant of the gradient descent, which we call it stochastic gradient descent, we just select from all of the data. Let's say these are the data. We select some of them, we call it a batch, and calculate the gradient just on those data and update the parameters based on the gradients of that batch. Okay, so as you could see in here, we called it stochastic gradient descent. So in this case, we just need to calculate the gradient on the batch. So if your batch size is 16, for example, but let's say you have 1 million data points, if you use the gradient descent, in each step you should calculate the gradient for all of 1 million data points. But if you use stochastic gradient descent with batch size of 16, you just need to calculate 16 gradient in each iteration of stochastic gradient descent, which is actually a really good thing computational wise. Okay, and we talked about model complexity and overfitting. We have seen that for the training data we could get 0 error, but if the model is really complicated, then the generalization error will be not good. For example, in this case, if we have this model, we could have a 0 training error, but if we have a test data in here, we have this much of error. But if we have this model, it could have larger training error, but the test error is actually better than this overfitted model. Okay. So we have overfitting when the model is so complicated. In other words, we have large number of parameters. So in this case, we may have a 10th order polynomial in here to get this complicated model in comparison with this line, which just have 2 parameters. And the second cause of overfitting is low number of training data. So if you have a low number of training data in comparison with the complexity of the model, then you will probably have overfitting. So in here we will see we could see an overfitting case for different polynomial order for fitting to this line. So it seems that there is an optimal polynomial degree to fit on this data. For example, in this case, the optimum polynomial degree is 3. So in this case, we are really close to the green line, which is the true data generating line in here. But if we increase the polynomial order, we will overfit to this data. But if we have lots of parameters, or if we have a complex model, but we increase the number of training data, we don't have an overfitting and we don't have a problem anymore. As you could see in here, if we have a 9th degree polynomial, but we increase the number of training data, in this case we don't have overfitting in contrast with this case anymore. So if you increase the training data, you could have a complex model without overfitting. So to avoid overfitting, we have seen that we should have a validation data set or test data set to see that whether our model overfitted or not. So we have 2 different methods. Simple holdout method, which we just put this for evaluation the model, and we have k-fold cross validation, which we talked about it in previous sessions. And another way to avoid overfitting is regularization. In regularization, we analyze the model complexity in the objective function. For example, we have seen that in linear regression, for example, we could add the second norm of the weights in the cost function. So this is a square error plus a regularization term to prevent the model to be really complicated and have high variance. And as we have seen, if we have the training data and the validation data, and if we plot the training cost function and the validation cost function based on the polynomial degree, we will see something like this, and for training data, and something like this for the validation data. And in here, in other words, in here we will start to overfitting, because the validation data growth but the training error decreases. So this is the optimal degree of polynomial. And also we talk about cross-validation, how to use it to evaluate the model and to obtain hyperparameters. And also about the regularization, as you could see in here, one way is to add the second norm or the first norm of the weights to regularize the model, and we call it ridge regression or weight decay, as we have seen and learned. And in here we could see an example of how the regularization could prevent the overfitting. So this was the regression. So in classification problem, we have some input data, but the output is discrete space. So the example is image classification. For example, we could have an image which is X, and maybe we want to know that whether it is, in this image we have a female or male. So this is a classification problem. Or for speech recognition, we have a similar task. And so this in two classes problem, we have something like this as the data points, and probably we want to find a classification model. Maybe it is something like this, which has these parameters to describe this line, and this could be the classification model. So if we have a data in which W transpose plus W0 is greater than 0, it means that it is in here. So the label will be the same as this data. Let's call them 1, and if it is less than 0, we could assign 0 or -1 to those data. Maybe you tell for the classification problem the square error loss function could work, but it is not actually really good for classification, because if you use the least square for the classification problem, and if you have this kind of data, because the distance between this line and this data are actually a lot, and in other words, the distance between this data and other data are a lot, then the line that you reach is not a very good point, is not a very good line, because the impact of these data are a lot on this line. But we know that these data probably not related to the decision boundary, and if we just ignore these data in here, we could see that we have maybe something like this based on just this data to have the classification model. And this is actually, we have seen that, for example, SVM just see at the support vectors to do the classification. Okay, I think for this session it is actually enough. We talk about the classification review a little more in the next session, and we continue our discussion. Hope you remember some of the stuff that we learned in the machine learning. So hope to see you in the next session. Bye.